When we move from stormwater detention to stormwater retention, we're talking about structural devices for stormwater infiltration into the soil, making permanent the storage of precipitation in the soil itself. This slide illustrates two different kinds of systems. In the upper left, we have what's called a Dutch drain, which takes downspout water, dumps it into a sediment trap where sediment from the roof off of which the water is flowing is captured. Periodically, the manager of the landscape comes in and removes the sediment to maintain storage capacity in the sediment trap. The remainder of the water flows over into a cistern, a dry cistern, and the cistern has permeable walls to it, which allows the water that is coming off of the rooftop into the sediment trap, moving eventually into the cistern, to be able to infiltrate into the soil. So in this sense, then, we're taking water off of the roof and immediately putting it into the soil. And hopefully, with enough infiltration capacity, then we're able to handle storm events of varying intensities. Then, when we hit a storm event that is beyond the capacity of this system to retain the water, then there is a valve that gets tripped by the fact that water is backed up here, and so the excess water discharges into the landscape. But a Dutch drain becomes a way of, for 90% of the storm events, trying to get that water to infiltrate into the soil. In the lower portion of this diagram, we see what's called a French drain infiltration. A French drain is a drain system that has a permeable surface to it. We can see here there's a checkerboard square that allows runoff to percolate through the grid pattern, and then the over surface has perforations in it. Here we see a modular block system. And both of these systems have a gravel underbasin. So water runoff then comes across the landscape, hits the French drain system, infiltrates into the soil, percolates down into the gravel trench, and eventually infiltrates down into deep water retention. So in this sense then, rather than temporarily storing the water, but releasing that volume just over a longer period of time, we're actually reducing the volume of water as well as the rate of water discharge. And in reducing the water, we have the capacity to allow the under drainage system and the surrounding landscape to provide water quality benefits. Stormwater retention also involves runoff from disconnected impervious surfaces and directing it into permeable cover. We can see in the left-hand image a concrete surface where runoff is flowing into a central drain and being discharged through a pipe into another landscape. The same concrete surface in the left-hand diagram is infiltrating, is running across the surface and infiltrating into a grassed portion or a vegetated portion of the landscape. So the amount of subsurface flow that's being generated by the left-hand image is considerably lower than the amount of subsurface flow that's generated by the right landscape. So not only are we increasing the rate at which water is going to be discharged, but we're actually reducing the volume of water that has to be dealt with. So we're retaining water where it falls, when it falls, and we're gradually restoring that water to the capacity of the landscape conditions in which we find ourselves. Here we see a plan view of a residence. The hatched area represents the roof of the residence. There's a parking lot, a permeable asphalt parking lot adjacent to it. The permeable asphalt parking lot has modular system of paving that allows runoff to infiltrate directly through the pavement rather than run off across the surface of the pavement. That water which does flow across the surface is directed into a seepage pit. The seepage pit promotes infiltration of runoff, retention of the runoff, rather than discharge of the runoff into surrounding landscape. And then there's an emergency drain for areas when we have excessive runoff. The capacity of the permeable parking lot is exceeded, the capacity of the seepage pit is exceeded, and so we have a retention pond that's designed to hold the water in extreme rainstorms when we don't have enough volume storage capacity. So here we see a chain of permeable paving with seepage pit with retention pond that allows us to deal more comprehensively with the volume and rate of runoff in the landscape. We see here 3 examples of parking lot conditions. The lower right-hand diagram is a parking lot that is graded to run all of the water from the parking lot down into this general vicinity. This is graded as a low point in the parking to receive most of the precipitation occurring from a 1 1/4 inch storm event. You may recall in a previous lecture I said that something like over 75% of storm events in Minnesota contribute less than 1 1/4 inch of rainfall. So if we can use parking lots as a way of storing that water and infiltrating that water back into the landscape, we are greatly reducing not only the rate of discharge but the volume of discharge. And in this case, that is accomplished by the modular paving systems that allow water to infiltrate, and the fact that this is the low portion of the parking lot from which water has drained, into which water has drained from higher portions. On the upper left and the lower left, we see cross-sectional diagrams of paving surfaces that are designed to promote infiltration. Here we see a gravel basin that infiltrates water into a gravel basin underneath of the parking surface itself. So we're actually using the undercarriage, the underground portion of the parking lot, as a means of storing the water by creating a very permeable material in it, in this case a gravel-based material. Same is true here, a gravel-based material that helps us then to collect the precipitation moving across the surface, infiltrate that into the landscape, and store it there permanently. So again, we're reducing rate, we're reducing volume, and we're retaining water in place. We're capturing water runoff in place and treating it right there.